In today's video, we'll be talking about momentum and its conservation. After watching this video, you should be able to understand how momentum is conserved in a collision and then the difference between an isolated and non-isolated system. So let's get right to it. There's this thing called the law of momentum conservation. And basically what that law says is that when two objects collide, that collision between the two objects, their total momentum, so if you look at the momentum of object 1 and the momentum of object 2, after they collide, the total momentum after the collision is equal to the momentum before the collision. Okay, so the total momentum before the collision is equal to the total momentum after the collision, no matter how you want to say it. Basically, momentum is conserved. So another way to write this would be that the total momentum lost by object 1 is equal to the momentum gained by object 2. And so momentum is conserved. And the word itself, conserved, means constant or not changing. Okay, so there's going to be no change in the momentum of the system. So let's take a look at an example of momentum, and I think this will, again, try to help explain what the law of conservation is all about. Now remember, the symbol for momentum is P, okay? And basically what it is that the total, and this is summation, that's what that stands for, this kind of like backwards looking E, the total initial momentum must equal the total final momentum. Okay, so the total initial must equal the total final momentum. Let's say I have two boxes, okay, and this box is 5 kilograms and it's moving at a speed of 3 meters per second to the right, and I have another 5 kilogram box. Notice they both have the same mass, and this one's moving at a speed of 3 meters per second to the left. Okay, so keep that in mind. They collide, okay, and so we'll have like boom. All right, so they collide, and after the collision, the two boxes are next to each other, and they really should be the same size. It's just I am not a good artist, and now they are at rest. Okay, they're not moving anymore. Okay, so you have these two boxes, they're running into each other, boom, they collide, and now they're at rest. Okay, one thing to keep in mind before I start to kind of talk about the conservation of momentum is momentum, this is a vector. Okay, it is a vector quantity. And so what does that mean? Well, basically, because it's a vector, we need to have a direction associated with our number value. Okay, so it has a magnitude and a direction. So before I begin to solve things, I'm going to say to the right is positive. Okay, I'm just going to kind of keep that in the back of my head, that to the right is positive. So let's calculate the total initial momentum of this system right here. Okay, what is the total initial momentum of this system right here, these two boxes? And I'm going to label these two boxes as box 1, and this will be box 2. Okay, very, very unique names. Okay, so let's calculate the total momentum. So box 1, remember the formula for momentum is mass times velocity. Okay, so 3 times 5 is 15. Okay, and this is positive 15. Why is it positive? Because this box is moving to the right. Okay, now what about the momentum of box 2? Well, 3 times 5 is 15, but this box is moving to the left, so it's going to be negative 15. Okay, and so if my math is right, positive 15 minus 15 is 0. Okay, so the total initial momentum is 0. Okay, so with that being said, the total final momentum, the total final momentum should also be 0 if everything is hunky-dory, if everything works out correctly. Okay, so let's do that math problem right here. Here's box 1, here's box 2. Remember, momentum is mass times velocity. Well, the mass of this box here is 5 kilograms, and it has a velocity of 0. 5 times 0 is 0. And then this box here has a mass of 5 kilograms and a velocity of 0. 5 times 0 is 0. So it does look like that the total momentum, or the final momentum, is 0. Okay, so it looks like the law of conservation has worked out. That is great. And so this is an example of how law of conservation of momentum works. Basically, the initial momentum of the total system has to equal the final momentum of the total system. And you can do some kind of cool things with that in terms of calculating the final velocity and all that good stuff. And I'll show you an example of that later on, and then actually the next video lesson goes into a lot more detail with that. Okay, so let's move on our merry way. Momentum is conserved for any interaction between two objects occurring in an isolated system. And that is a key thing here, that we need to have the system being isolated. And so what is something that's not isolated? Here are basically the criteria or the examples of non-isolated systems. If you have a force that originates from a source other than the two objects of the system, so for instance, in that box example, had I had some like random person come in and push the box, one of the boxes afterwards, that would be non-isolated. And then a force that is not balanced by other forces. And so an example of this would be like something like friction. Okay, friction typically isn't balanced by another force. It's typically just there, and it slows objects down. It stops the movement of objects. Okay, so if you have anything like that, if you have friction, or if you have like some random force coming in from a source other than the two objects of the system, then it's not isolated. Okay, so for most of our problems, we'll be dealing with isolated systems where it's friction-free, air resistance-free, and we can do some calculating with using the law of conservation of momentum. So you may say, well, how can we just, ignore friction and air resistance? Friction and air resistance in basically any real collision do not cause a huge distance or difference to the system. It's pretty close to being perfectly isolated. Like if you think about like two cars running into each other, the amount of friction between the road and the tire of the car actually slowing the cars down and messing with the system of that car crash is probably pretty minimal compared to other factors in the collision. Okay, like the forces of the two cars hitting each other and that kind of thing. The force of friction, the force of air resistance on the car is really not going to cause the two cars to slow down that much. It's going to be really insignificant, because if they were significant, then we probably would actually be a little more concerned about it. Okay, so air resistance and frictional forces are so minimal compared to the contact forces in a collision, we basically, for the most part, can say, well, we'll ignore those for right now. We just want to get a general understanding and a good grasp of what it means to conserve momentum. Okay, so here are some examples of things where you want to kind of keep an eye open for, like where maybe the system isn't isolated and you need to kind of think about things differently. So here are some examples. It says two cars collide on a gravel road where the frictional forces are pretty dang large. Okay, is that an isolated or not isolated system? Well, here is an example where frictional forces are large, and so this is not isolated. Okay, if you have large frictional forces, then it's no longer isolated. We probably need to actually account for that frictional force in terms of its opposing motion. Okay, friction basically opposes motion, and so we would need to account for that. Your mom is pushing a vacuum cleaner across the living room carpet, and we'll say this carpet's relatively, plush and thick. Is that isolated or not? Well, again, if your carpet's pretty thick, this is not isolated because the frictional forces of the carpet are pretty dang strong. And so that's going to oppose the motion of the vacuum cleaner, and so you don't really have an isolated system there anymore. Here it says a block of ice hits another block of ice on a frozen pond. Okay, if you think about ice is relatively friction-free, and then this is partly why people slip on ice, is because there's a lack of friction between your shoes and the ice. So this would be an example of an isolated system. Those two blocks of ice, when they hit each other, are basically going to be just the only forces acting upon them are going to be the forces of each other hitting one another. Okay, there's no frictional force. Air resistance is relatively minimal, so you would say that is an isolated system. Okay. Let's do one more example problem on dealing with momentum, and then I think you guys will basically have things down pretty well. It says a 15-kilogram ball is thrown at a velocity of 3 meters per second to a 60-kilogram person who is at rest on the ice. The person catches the ball and slides on the ice. Determine the velocity of the person and the ball. Okay, I highly recommend first writing down what you know. Okay, so I'll call it the mass of the ball, or m sub b, is 15 kilograms. And the velocity of the ball is 3 meters per second. And we'll say it's traveling to the right. So I'll make that positive, just because I like dealing with positive numbers. The mass of the person, or the MP, is 60 kilograms. And the velocity of the person, it says they're at rest. So they have a velocity of 0 meters per second. Okay. Now, remember, momentum is a vector, and so that's partly why I'm doing this plus piece here. And it is conserved. And the reason why it's conserved is because this is an isolated system. This is basically a person standing on ice, so we can assume it's relatively friction-free. I'm going to just draw a quick picture here, just to kind of get us an example here. Here's this ball coming in this way. Here's this person. We'll have them catch it, not have them hit it in the head. With their arms ready to catch this ball, okay? So this is right before the collision, okay? What is the total momentum of that system, okay? Well, remember momentum, the formula for momentum is m times v, right? So 15 times 3 is 45, plus what is the momentum of this person, okay? What is the momentum of this person? Well, 60 times 0, anything times 0 is 0, so plus 0. Equals the final momentum. Now, what is the final momentum? Well, that is the mass of the ball times the velocity of the ball and the person. And the reason why I'm saying velocity of the ball and the person is because it's going to be the same velocity, okay? Because he catches the ball, right? And so they're going to be traveling together as a whole unit now. Plus the mass of the person and times the velocity of the ball person duo. And if you know your algebra, basically what you're seeing here is we can do a little bit of like separating out here. We can say basically that mass of the ball plus mass of the person times the velocity of the ball and the person. Right? I just basically pulled out the velocity piece so that it's outside of the parentheses, is equal to 45. Now, what is the mass of the ball? Well, it's 15. And what is the mass of the person? Well, it's 60. And so if I do that addition problem real quickly in my head, I would get 75 equals 45. And then I'm just going to drop down velocity of ball person. And if you do that little algebra problem, 45 divided by 75, I get a velocity of 0.6 meters per second, okay? Which is pretty slow. I mean, that's not fast, but this kind of makes sense. If you throw a ball, the ball initially is going faster, right? Well, how come? Basically, it's because the ball doesn't have a huge mass. But now, all of a sudden, the ball's got to be pushing itself and the person, right? And so the velocity definitely should go down. So the numbers do seem to make sense in terms of that the velocity would decrease. So this person is probably going to slide to the right a little bit, not a lot, but a little bit, actually at a velocity of 0.6 meters per second. That takes care of this video. I will see you guys next time.